Neuromorphic computing is an exciting field that seeks to mimic the structure and function of the human brain using computer hardware and software. Unlike traditional computers that process information sequentially, neuromorphic systems are designed to process data in parallel, much like our own neural networks. This approach allows for more efficient, adaptive, and intelligent processing, opening up new possibilities in artificial intelligence and machine learning. By drawing inspiration from biology, neuromorphic computing aims to overcome some of the limitations of conventional computing, such as high energy consumption and limited scalability. In this video, we'll explore the core concepts, benefits, and real-world applications of this groundbreaking technology. Human brain is a marvel of efficiency and adaptability. It processes vast amounts of information using billions of neurons and trillions of connections, all while consuming very little power. Neuromorphic computing takes inspiration from this biological wonder, aiming to replicate its parallel processing and learning capabilities. By studying how the brain manages tasks like pattern recognition and decision-making, researchers are developing new hardware and algorithms that can perform similar functions. This brain-inspired approach is at the heart of neuromorphic computing, setting it apart from traditional digital systems. Traditional computers rely on the von Neumann architecture, where memory and processing are separated. This creates a bottleneck limiting speed and efficiency. Neuromorphic systems, on the other hand, integrate memory and processing much like the human brain. This integration allows for faster data transfer and lower energy consumption. As a result, neuromorphic computers can handle complex, data-intensive tasks more efficiently than their traditional counterparts. Understanding these differences is key to appreciating the potential of neuromorphic technology. In the brain, neurons communicate through electrical impulses and chemical signals. Each neuron receives inputs, processes them, and sends outputs to other neurons. This network of connections enables learning, memory, and decision-making. Neuromorphic computing tries to replicate this process using artificial neurons and synapses. By modeling these biological processes, neuromorphic systems can learn from data, adapt to new situations, and perform complex tasks with remarkable efficiency. Neuromorphic hardware uses artificial neurons and synapses to process information. These components are designed to mimic the way biological neurons and synapses work, allowing for parallel processing and adaptive learning. Artificial neurons receive signals, process them, and pass them on just like their biological counterparts. Synapses, which connect neurons, can strengthen or weaken over time, enabling the system to learn from experience. This dynamic structure is what gives neuromorphic systems their unique capabilities. Key feature of neuromorphic computing is the use of spiking neural networks, or SNNs. Unlike traditional artificial neural networks, SNNs process information using discrete spikes, similar to the way real neurons communicate. This approach allows for more efficient and realistic modeling of brain activity. Spiking neural networks can handle complex time-dependent data, making them ideal for tasks like speech recognition and sensory processing. One of the biggest advantages of neuromorphic computing is its energy efficiency. By mimicking the brain's low-power operation, neuromorphic systems can perform complex computations using a fraction of the energy required by traditional computers. This makes them ideal for applications where power consumption is a critical concern, such as mobile devices, robotics, and edge computing. As energy demands continue to rise, neuromorphic technology offers a promising solution. Neuromorphic systems excel at real-time processing, handling sensory data as it arrives. This capability is crucial for applications like autonomous vehicles, robotics, and smart sensors, where quick decision-making is essential. By processing information in parallel and adapting on the fly, neuromorphic computers can respond to changing environments with speed and accuracy. This real-time adaptability sets them apart from traditional computing systems. Standout feature of neuromorphic computing is its ability to learn and adapt. Just like the human brain, neuromorphic systems can adjust their connections based on experience. This means they can improve performance over time, handle new situations, and even recover from errors. This adaptability is especially valuable in dynamic environments, where conditions can change rapidly and unpredictably. Developing neuromorphic hardware requires innovative materials and designs. Researchers are experimenting with new types of transistors, memristors, and other components that can mimic the behavior of neurons and synapses. These advances are making it possible to build chips that are faster, more efficient, and capable of supporting complex neural networks. As hardware continues to evolve, the potential of neuromorphic computing grows even greater. In addition to hardware, neuromorphic computing relies on specialized software. This software is designed to manage the unique architecture of neuromorphic chips, enabling efficient communication between artificial neurons and synapses. Programming these systems requires new approaches, as traditional software models don't always translate well to brain-inspired hardware. As the field matures, more tools and frameworks are being developed to support neuromorphic application. Robotics is one of the most promising areas for neuromorphic computing. By enabling robots to process sensory data in real time and adapt to new situations, neuromorphic systems can make machines more intelligent and responsive. This technology is being used in everything from autonomous drones to robotic arms, helping robots navigate complex environments and perform delicate tasks with precision. Neuromorphic computing is also transforming the world of smart sensors and the Internet of Things (IoT). By processing data locally and efficiently, neuromorphic chips can enable sensors to analyze information on the spot, reducing the need for constant communication with central servers. This leads to faster responses, lower energy use, and greater privacy for users. As IoT devices become more widespread, neuromorphic technology will play a key role in their evolution. Edge computing refers to processing data close to where it's generated, rather than sending it to distant data centers. Neuromorphic chips are ideal for edge computing because of their low power requirements and real-time processing abilities. This makes them perfect for applications like smart cameras, wearable devices, and industrial automation, where speed and efficiency are critical. Healthcare neuromorphic computing is opening up new possibilities for diagnostics and patient care. By analyzing medical data in real time, neuromorphic systems can help doctors detect patterns and make faster, more accurate decisions. This technology is being explored for applications like early disease detection, personalized treatment plans, and advanced medical imaging. Autonomous vehicles rely on fast, accurate processing of sensory data to navigate safely. Neuromorphic computing provides the speed and adaptability needed for these vehicles to interpret their surroundings and make split-second decisions. By mimicking the brain's ability to process complex information, neuromorphic systems are helping to make self-driving cars safer and more reliable. Neuromorphic systems excel at tasks like speech and vision recognition, where real-time processing and adaptability are crucial. By modeling the way the brain interprets sensory input, these systems can recognize patterns, understand language, and even identify objects in complex environments. This makes them valuable for applications ranging from virtual assistants to security systems. Despite its promise, neuromorphic computing faces several challenges. Building reliable, scalable hardware is complex, and programming these systems requires new skills and tools. There are also questions about how to best integrate neuromorphic chips with existing technologies. Overcoming these hurdles will require continued research and collaboration across multiple fields. Research in neuromorphic computing is advancing rapidly. Universities, tech companies, and government agencies are investing in new materials, architectures, and algorithms. Collaborative efforts are driving innovation, with interdisciplinary teams working to solve the technical and practical challenges of building brain-inspired computers. As research progresses, we can expect to see even more breakthroughs in the coming years. Several major companies are leading the way in neuromorphic computing. Firms like IBM, Intel, and Google are developing specialized chips and software platforms to harness the power of brain-inspired computing. These industry leaders are partnering with academic institutions and startups to accelerate the development and adoption of neuromorphic technologies. Open-source projects are playing a vital role in advancing neuromorphic computing. By making hardware designs, software tools, and research findings freely available, these initiatives foster collaboration and accelerate innovation. Open-source communities are helping to lower barriers to entry, enabling more researchers and developers to contribute to the field. As neuromorphic computing grows, education and training are becoming increasingly important. Universities are developing new courses and degree programs to prepare students for careers in this emerging field. Online resources, workshops, and conferences are also helping professionals stay up to date with the latest developments and best practices. With any powerful technology, ethical considerations must be addressed. Neuromorphic computing raises questions about privacy, security, and the potential impact on jobs and society. Researchers and policymakers are working together to develop guidelines and regulations that ensure the responsible development and use of neuromorphic systems. Neuromorphic computing is poised to transform the future of artificial intelligence. By enabling machines to learn, adapt, and process information more like humans, this technology could lead to smarter, more capable AI systems. As neuromorphic hardware and software continue to advance, we can expect to see AI applications that are more efficient, flexible, and intelligent than ever before. Reducing energy consumption is not just about efficiency, it's also about sustainability. Neuromorphic computing's low power requirements can help reduce the environmental impact of data centers and electronic devices. By making computing greener, this technology supports global efforts to combat climate change and promote sustainable development. Neuromorphic chips can complement cloud computing by handling data processing at the edge, reducing the load on central servers. This integration allows for faster, more efficient services, especially in applications that require real-time analysis. As cloud and neuromorphic technologies evolve, their combined power will unlock new possibilities for businesses and consumers alike. Neuromorphic computing can enhance security by enabling devices to detect anomalies and respond to threats in real time. By processing data locally and adapting to new attack patterns, neuromorphic systems can provide a more robust defense against cyber threats. This makes them valuable for applications in finance, healthcare, and critical infrastructure. By learning from user behavior, neuromorphic systems can deliver more personalized experiences. Whether it's recommending content, adjusting device settings, or anticipating needs, these systems can adapt to individual preferences over time. This personalization enhances user satisfaction and makes technology feel more intuitive and responsive. Neuromorphic computing has the potential to make advanced technology more accessible worldwide. By reducing energy and hardware requirements, it can bring powerful computing to remote and underserved regions. This democratization of technology can help bridge the digital divide and promote economic development on a global scale. As we look to the future, neuromorphic computing stands out as a transformative force in technology. By harnessing the power of brain-inspired design, we can create machines that are smarter, more efficient, and more adaptable than ever before. The journey is just beginning, and the possibilities are truly limitless. Stay tuned as neuromorphic computing continues to shape the world of tomorrow.